In this video, I am going to explain acceleration diagram of 4-bar mechanisms using the relative velocity method. Let us see that problem. In a 4-bar kinematic chain ABCD, dA is fixed and is 150 mm long. The crank AB is 40 mm long and rotates at 120 rpm clockwise with 2 radians per second square angular acceleration, and while the link CD is equal to 80 mm oscillates about D. So BC and AD are of equal length. Find the angular velocity of the link CD and acceleration of point C when angle BAD is equal to 60 degrees. So this is the diagram is given. Now we want to first construct the velocity diagram, then so after getting the velocity diagram, then we are going to construct the acceleration diagram. So in my previous video, you may watch to know how to construct the configuration diagram and velocity diagram. So that is velocity diagram of 4-bar mechanism that YouTube you may watch, and you can know that stepwise procedure I explained in that video. Now directly I am going to explain acceleration diagram in this video. So before going to draw the acceleration diagram, first of all we need to find out the acceleration of all the points. And all these, because this vector is having the both magnitude and direction, so we need to get all the information before going to draw the acceleration. So for that purpose, just I prepared this tabular form. The tabular form consists of the first column is acceleration, second column is what type of acceleration, third column is indicates that vector representation, and fourth column is the magnitude, and fifth column is direction, and the sixth column is sense. Once if any vector this information is known, then you can easy to draw the vectors. Now let us see that. First find out acceleration of point B with respect to A. So this acceleration is known as radial acceleration or centripetal acceleration. So the vector representation of this F to the power of FCBA, that is equal to A1 X bar, where X is the intermediate point. And how you are going to find out the magnitude, that is V square BA by BA. So V square BA is the vector AB. You can take this vector AB from the velocity diagram and square that value divided by capital AB. This value you can take from the configuration diagram. Then you can find out the magnitude of this radial component of acceleration. Then what is the direction of this component? It's parallel to that link AB, parallel to link AB, and sense is because of the centripetal type of acceleration, the acceleration is acting towards center of rotation. So then this will act the B to A, the sense is towards A. So once if you know this vector A1X, both magnitude, direction and sense, then you can easy to draw this vector. Okay. And coming to the next component of acceleration, it's a tangential acceleration. It's representing FTBA, that is equal to XB1 bar. So the vectorial sum of these two gives the vector of that A1 B1. That is the final the acceleration vector for the acceleration of B with respect to A. So the magnitude is alpha into AB. The direction is perpendicular to AB and the sense is in the direction of the link rotation. Now coming to the second component of acceleration, the acceleration of point C with respect to B. Now assuming the point C on the link BC, then we can find out the acceleration of C with respect to B. It's also having the two components, radial acceleration. The vector notation is FCB, that is a B1 to Y bar, and the magnitude is V square CB by BC, the vector BC whole square by capital BC. The vector BC take from the velocity diagram and capital BC from the configuration diagram and find out the magnitude, and the direction is it's perpendicular to BC and the sense is C towards B because B is the center of rotation. Then the tangential acceleration. The tangential acceleration will represent the vector is YC1 and magnitude is unknown. Direction is it's perpendicular to BC and the sense is also unknown. So now coming to the point C, now assuming on the link CD, then find out the acceleration of C with respect to D. It's also having the two components, radial acceleration, the vector representation is D1 to Z and the magnitude is v square cd by cd, that is equal to dc square by cd, and the direction is parallel to cd, and the sense is c to d. The tangential acceleration, so the vector representation is FCD, that is equal Z to C1, then it's unknown magnitude, direction is perpendicular to CD, and sense is unknown. So now with this information of all the vectors, now we can able to draw the acceleration diagram of this 4-bar mechanism. Now let us once completed all the information, let's go for drawing the acceleration diagram. Now let us see that already we have constructed the configuration diagram and velocity diagram. Then we will go for the acceleration diagram. So better you can follow that all the diagrams in one paper or one sheet, so that we need to draw the parallel and perpendicular lines are very easy to draw it. That's why I am keeping that one page, the configuration diagram, velocity diagram. Then I am going to draw the acceleration diagram, the stepwise procedure. Let us see that. First, you have to mark the convenient point and assign all the fixed points to that point. Here in this mechanism, what are the fixed points? A and D are the fixed points. Now assign this point, convenient point, according to plan. The space of the paper is available, and mark the point and assign these 2 points, A1 and comma D1. Here, because in this velocity diagram already used a small a, b, c, d. In acceleration diagram, I am using the small a1, small b1, small c1 like that. So now I assign the a1 and d1. Now first draw the vector, that is the radial component of b with respect to a. Okay. So now this vector is parallel to BA and magnitude is given. So now we draw this vector. This is the FCBA. Now draw the tangential component of acceleration from x to b1. This vector is FTBA. Now joining these 2 points a1, b1, this is the final vector of b with respect to a. Final vector of b with respect to a. Okay. Now next coming to the acceleration of point c with respect to b. So now first draw the radial component of acceleration. Now you can see that from b1y, that is parallel to the link bc, and with the given magnitude draw this vector. This is the radial component of c with respect to b. Then you can draw the perpendicular to this, perpendicular to link BC, that is the tangential component of B with respect to C up to certain length. Because length is unknown, magnitude is unknown, you can draw the up to certain length. Okay, on this line somewhere the point C1 is lying. Okay, now coming to this C, considering on the link CD, then find out the radial component of C with respect to D. So now you can draw this vector. You will see that that is from the D1 to Z. This is the radial component of C with respect to D. Now draw the tangential component, the perpendicular to this vector or perpendicular to link CD, and this line and previous line, that is FTBC, both will intersect. That intersection point mark as a C1. Okay. Then this is the vector tangential of component of C and D. So once the C1 is known, then you can join A1 C1 and B1 C1. So now B1 C1 is the vector total acceleration of point C with respect to B, and this C1 D1 is the total acceleration of C with respect to D. So now this is the required acceleration diagram. Okay. So once if you know the acceleration diagram, from that what we want, we are going to find out. In the problem is asking what is the acceleration of point C. Is not mentioned this acceleration with respect to any other point. So then if not mentioned, we are assuming that it's absolute acceleration and take the values from the fixed points. Here what are the fixed points? A1 and D1 are fixed points. Then to measure the distance between C1 and D1, that gives the acceleration of C with respect to D. So after measuring, then multiply whatever the scale you taken for constructing the acceleration diagram, that gives the acceleration of point C with respect to D. I hope all of you understand how you are going to construct the acceleration diagram. Okay.